Hello, and welcome to lesson number 45, Fission and Fusion. One thing that can be a little bit confusing when we talk about these two is kind of like what's the difference? Just before we actually get deep into everything, the simple idea is that fission is breaking apart something big into smaller pieces. So the example I'm going to be using a few times is you take a cookie and you snap it in half to share it with a friend. In fusion, we take small things and we try to smash them, well, fuse them together into something bigger. And that is comparatively much more difficult. Imagine taking the two broken pieces of cookie and trying to put them back together. It's just not going to happen very well. But just keeping that in mind as we start going through this, it is the fundamental difference between the two, and it's kind of the starting point for us. So going into fission, what we have to assume is that we're starting with a rather large nucleus where the total number of nucleons is probably bigger than about 120. When it splits apart, there is a small mass defect. Well, I shouldn't say small, but there is a mass defect, and that releases energy. Good old classic E equals mc squared. The thing is, this is actually relatively easy to do. If we start with something like uranium-235, which is not exactly a super common isotope, but we can refine it out and enrich the uranium that we do dig out of the ground until we have some uranium-235, it's itself pretty darn stable. But when we get it to absorb a neutron, it becomes highly unstable uranium-236. That's the cookie that's going to break for us. We don't really have to do much. We just have to have enough uranium-235, a piece physically big enough that the probability of just a random neutron flying around the room, hitting it and being absorbed by one of those uranium-235 nuclei is highly, highly probable, then it will become that uranium-236 and do the splitting for us. So a way that I can kind of visually show this to you there is nice, simple uranium-235 nucleus just sitting there, and there's the neutron coming in towards it. It gets absorbed, and we form uranium-236, which is going to exist for only a fraction of a second. Okay, it's not going to be there for much time at all until it fissions. And in this example, I'm saying that we get some barium-141 and some krypton-92, and 3 neutrons go flying off, plus the energy, the cookie crumbs that have turned into energy in this case. Now, this is not a great way to show it because it doesn't let us see all the conservation of nucleons and conservation of charge. So it would be better if we did write it out in sort of a more standard format. So looking at it here, it's the exact same thing. It's the uranium-235 that we start with, absorbing a single neutron to form uranium-236, super unstable, so it almost instantly fissions into the barium-141, krypton-92, and look carefully at that last thing there. It is 3 individual neutrons. So the way that we're writing it there with this 3 at the beginning is as a coefficient effectively to say that there are 3 of those neutrons. Okay? Now, this is just one way that that cookie can break, because if you snap a cookie, sometimes the pieces you're going to get are going to be slightly different sizes. Oh, and sorry, I should have mentioned, if you do take a gander here at conservation of charge and conservation of nucleons, 56 plus 36 plus 0, doesn't really matter, gives us the 92, and 141 plus 92. Now be careful here because it's 3 times 1, so that's 3 there with the neutrons. That gives us our 236. So conservation of charge and nucleons is working across everything totally fine, just the way we would expect it to. But like I was saying, let's crack this cookie a different way. We could also get something like this, where we still do the same start. We get to the uranium-236, it fissions, but this time we got xenon-140, strontium-94, and notice only 2 neutrons. I don't even have to show you that there's 2 neutrons because you could go ahead do some conservation of nucleons up here, and if you do 140 plus 94, you only get 234. So where's the other 2? It must have flown out because of 2 neutrons being released. So one way to kind of look at this is that when we break up the uranium-236 through fission, sometimes we might get 3 neutrons, sometimes we get 2, and certainly there's other combinations besides these 2 that I'm showing you here. But what we found is, on average, all of these fissions of uranium-236 usually release about 2.5 neutrons on average. Now, obviously we can't have half a neutron, but we're just saying that's kind of what we predict to see. Sometimes 2, sometimes 3, maybe sometimes even more or less, but on average 2.5. So how can we actually use this to our advantage? Well, one thing that was kind of realized early on is it kind of sucks if we have to keep on trying to set up the right circumstances to hopefully get 1 neutron to just be whizzing around and bump into a uranium-235 nucleus for us. So how's about this? What if out of these 2.5 on average neutrons here, we let, hopefully by just setting up the relative amounts of uranium-235 nearby and all the factors that we can possibly control, what if we made it highly probable that 1 of those 2.5 neutrons would actually hit into a uranium-235 nucleus afterwards, making uranium-236, producing XY, some, broken up pieces smaller than the uranium-236, plus again 2.5 neutrons. And we keep letting that happen. We keep setting it up so that we have a high probability of 1 neutron from each previous reaction interacting with the next uranium-235. This is a critical chain reaction. Each reaction leads to 1 more reaction. A good way to think of this is if you have a big long row of dominoes set up, and you might have like 20 or 30 of them, you're not knocking down each domino, you just knock down the first one, and then each one after that falls over, and it just keeps on going on its own. Critical, sometimes, when we hear the word critical, like if you're watching a hospital drama on TV, critical is bad. If they say the patient is critical. But here, this is a self-sustaining fission reaction. If I've got a nuclear power plant and I just want it to keep going, I want the reactor to be critical like this. But what happens if we don't have just 1 neutron from each reaction leading to the next? Then we get a supercritical chain reaction. So that means that when I have the first reaction happen and it produces 2.5 on average neutrons, I actually let more than 1 of them bump into other uranium-235s. So 1 reaction could lead to 2 new reactions, which could lead to a couple more each, and so on and so on. We would effectively get exponential growth. 1 that we allow to start becomes many, many more with each later generation, if you think of it that way. This is what we would want to have happen if we are starting up a nuclear reactor and we need to get the total number of reactions building up to a point where then we would kind of pull things back and get it to the point of being critical. Or this is honestly what you want in a nuclear bomb also, because 1 leads to many, and all of a sudden the whole thing just is giving off huge amounts of energy in a rush. But we can also have a subcritical chain reaction. Maybe we're shutting down the nuclear reactor, and to think of this, imagine you've got a whole bunch of different rows of dominoes falling over, and you start pulling out some of those dominoes. You're interrupting the flow of neutrons getting to the next reaction, so that over time, the total number of reactions dies out until, if you've pulled out enough of the dominoes, you've pulled out enough of the neutrons, then it just dies off. So how are we going to actually do this? How are we going to have it so sometimes the reactor is critical and sometimes supercritical or subcritical? Because in a regular nuclear reactor, we would need to be able to do all of those things at different times. The answer is control rods. Control rods are typically elements like boron or cadmium, and these elements, at least if you have the right isotopes, will absorb neutrons. If those control rods made of those elements are absorbing the neutrons, you could push them deeper into the core. They'll absorb more of the neutrons, like sponges soaking up water. And if they're absorbing more of the neutrons, it's neutrons that don't get to go to the next uranium-235, and that's going to slow down the reaction and make it subcritical. But maybe if the reactor is maybe starting to go too subcritical, or maybe you need it to speed up and have more reactions happening, you want a little bit of supercritical happening, then you could pull the rods back out a bit. Kind of a visual way of seeing this would be like this. The control rods are in purple. The uranium in rods down in a pool of water, so there's something to absorb all that energy and probably run a steam turbine. But the control rods are only partially inserted into that core right now, and with it set up this way, we can expect, on average, 1 neutron getting from each previous reaction to the next. So we have a critical reaction and everything's going along tickety-boo. Now, if I want to go subcritical, I push those control rods deeper in. They're going to be doing a better job of soaking everything up now, because now there won't be as many neutrons getting to the next uranium-235. We're actually going to drop the power output from this reactor at this point, and if we keep it up, eventually it'll just stop. If we want it to be supercritical, we pull those rods back out, in fact quite a bit, so that on average we're getting more neutrons, more than one reaching from each previous fission reaction to the next, and our power output would be getting greater and rising. Now, again, this is all great until you face other problems, because when the very first nuclear reactors were being developed at an experimental level, they noticed a problem. The neutrons that were being emitted from the previous nuclear fission were simply moving too fast. They would hit the uranium-235s, but they would bounce off like a rock skipping off of a lake. So the solution they came up with is we need the neutrons from the previous fission to hit something that's roughly the same size in order to get them to move at a slower speed, and then they'll have a chance to interact with the uranium-235 they're supposed to be absorbed by. They needed something, though, that would be roughly the same size, because we want to kind of, slow them down but not stop them, and we actually want to have an effect on them. If you're walking through the hallway of the school and a mosquito flies in front of you and you bump into it, the mosquito's too small, so you don't even notice, you don't slow down. But if you bump into another person, you will slow down. You might also change your path of motion a little bit, but you'll slow down. It might actually cause them to move a little bit. But what they were looking for was something they could bump into that's roughly the same size as a neutron. That means probably we should be looking for protons, right? They're about the same size. Well, what is there that is an easy source of protons? Well, one thing would be the hydrogen in water, because hydrogen itself is basically a proton with an electron whizzing around it. At least hydrogen 1 is. So this seems like a great solution. Water is super easy to get. Each water molecule has 2 protons just hanging out there for the neutrons to hit. This is great, except for a small problem. The hydrogen ones that make up most of the water that we would deal with actually have a tendency to absorb neutrons in this themselves. So if they absorb the neutrons, they're not going to continue on their merry way to be absorbed by uranium-235. The way to get around this is to make sure that the uranium that you're using in your reactor is even a higher percentage of uranium-235. Enriched uranium-235 is what we would call this. That means that even though a bunch of the neutrons will get absorbed by the water, some of them will just hit and slow down. We just have to give them a really high probability of next bumping into uranium-235 nuclei. So we just have that higher percentage. This is the process that is favored by the United States. A different suggestion then is to start with water where the hydrogens have already absorbed that extra neutron. Now, that hydrogen is special because it's already absorbed an extra neutron. Its A value is 2, and so it's quite often referred to as deuterium. And the water that has deuterium hydrogens on it is referred to as heavy water because each water molecule is carrying 2 extra neutrons. It is ever so slightly heavier. And this is measurable. We can actually see this when we do things like separate out heavy water from regular water. Every day when you're drinking water, there will be randomly some heavy water molecules in there. Don't worry, your body at a chemical level still uses them exactly the same way, and they're not radioactive or something like that. It naturally occurs anyways. So if we do this, if we go to the trouble of separating out the heavy water from the regular water, and then we use heavy water in our reactors, we can actually go back to using regular uranium-235. This is the process used by Canadian-designed reactors, CANDU reactors, Canadian Deuterium Uranium. And actually, CANDU reactors have a wonderful history around the world of very high reliability and high safety. So we actually sell and build nuclear reactors in other countries. Third option, carbon rods. I know this might seem a little bit weird, but totally by a fluke, carbon actually does do a pretty good job of slowing down neutrons as well. Great thing about carbon rods is it's really super cheap and easy to get also. Burn down a tree, squish it all the ashes and stuff together to make something that looks sort of like a charcoal briquette. You've got carbon rods. And you can still use regular uranium-235. Problem, if ever even the smallest bit of oxygen gets into where you've got this all set up, those carbon rods will act kind of like charcoal briquettes because they'll burst into flames. And essentially, along with other things that were happening that day, this is what happens at Chernobyl. So kind of a scary thing. Basically, any country that was part of the former USSR uses this carbon rod system, and also Britain uses it.